It is a section 15.2, double integrals over general regions. Now we know how to find the volume of the solid on the surface when the solid is based on a rectangular region. In this section, we'll generalize the technique for iterated integrals over general regions. Consider this boundary region of general shape D. What we want to find is the double integral over D of f of xy. In order to find the integral, first we expand the domain to a surrounding rectangle R, as in this figure, right side, and we define capital F, whose value is the same as f of xy when xy is in D, otherwise the value is 0. So capital F is the same as f inside and outside, the value is 0. And then we can easily see that double integral over D of little f is the same as double integral over R, capital F. But for this integral, we know its existence, and also we know how to get it. In fact, we can use an iterated integration to get this value. So we can conclude the following. The integral, double integral over D of f exists for a general bounded region D. And the iterated integral can be applied to get the double integral. Now we'll consider some special cases. For example, x is moving from A to B, and for each x, y is moving from g1 of x to g2 of x, like that. So that once x is moving from here to there, and for each x, we are covering the domain vertically, and then eventually we can cover the domain without duplication. So in this case, we may try to get integral in this way. Now x is moving from A to B, so it's an out integral. And for each x, y is moving from g1 of x to g2 of x. So that is the corresponding integral. The other case, now y is moving from C to D, and for each y, x is from h1 of y to h2 of y. So we can cover the domain horizontally, like that. The corresponding integral is given in this way. Now y is the outer integral, C to D, and for each y, x is moving from h1 of y to h2 of y, and we can get this inner integral first and then outer integral. Here we have a strategy for double integral over general regions. First, you have to visualize to recognize the region and decide the order of integration. If for given order the calculation becomes complicated, then try the other order. Let's try to solve some problems. Evaluate this double integral where D is the region bounded by the line and the parabola. X is y squared. Let's try to visualize the domain, the region. Okay, this is y-axis, that is x-axis. Now, y is x minus 2. That is like that. That is y equals x minus 2. And x is y squared. That will be a parabola of this shape. Okay, passing this origin and coming out. So that is x is y squared. So bounded by these two curves, that means this is the region. Okay, that is D. We have to access this domain systematically. Possibly, okay, y is moving from here to there. And for each y, now x is moving from here to there, right? Okay. So we have to find this point and that point. And that is, from this one we have x is y plus 2. And from this one, x is y squared. So that we have y squared equal y plus 2. That means that is y squared minus y minus 2 equals 0. So here y minus 2 and y plus 1 equal 0. So we have y equal 2 and minus 1. That means that is minus 1. This position is 2. Okay. So if we try to get the integral with y integral out integral, then the given integral must be same as from minus 1 to 2, that is y direction. And now we have to get x direction. Okay, for each y, and x is moving from here to there. What is this one? That is exactly that one. So bottom must be y squared. This is a bottom x, top x. That is this one. Here x is y plus 2. Y plus 2. That is bottom x, top x. But you have to express it as a function of y. Now, that is 2xy and y direction first. And out integral is x. No. That is, okay, I'm sorry. Okay, that is x direction in the integration and out to y integration. Okay, now we'll focus on the inner integral. Okay, then that is from minus 1 to 2, and that is x squared y. Y is constant, and we have x squared. X is moving y squared to y plus 2. And after getting this one, we'll try to get y integration. Okay. For that one, minus 1 to 1. Okay. That is y times. Now, okay, from this one, this is squared. Okay, y times and y plus 2 squared minus y to the 4, okay, dy. So, okay, that one is minus, okay, that is 2, minus 1 to 2, and we have, that is, okay, first there is y squared times y, so the y cubed, okay, and 2y, so there is 2y squared, and 4y, and minus y to the 5 dy, right? Okay, From this one, 1/4 of y to the 4 plus 2/3 y to the 3 plus 2y squared minus 1/6 y to the 6. Okay, and we have to evaluate from -1 to 2. Okay, for that one. Okay, and from now on it's a simple algebra, and you will get the value 45/4. That's the final answer. Okay. Okay, let's go to the next problem. Find the volume of the solid that lies under the plane Z is 1 plus 2y, and over the region D in the xy plane bounded by the line y is 2x and parabola y equal x squared. Okay. As for the previous problem, you have to visualize the region. You have to recognize the region so that you can access. Okay, that's x direction, y direction. Now, y equal 2x is a line passing the origin, and like that. So that is y equal 2x. And y equals x squared is given in this way, the parabola. Oops. Okay, let's try again. Okay, go down and go up, like that, right? So that is, this one is y equal x squared. So region D is this one, that is D. Okay. And we have to get integral z equal 1 plus 2y. So that is a double integral over D and 1 plus 2y and dA. This is what we have to get. Now, to get the solution, we may access this domain either x direction outer integral or y direction outer integral. So either way, we can access the domain easily and systematically. So first, let's try to find this intersection. From this one, y equal x squared. From that one, y equal 2x. So that is x squared equal 2x, which means that x is either 0 or 2. So this is 0, and this one is 2. Then y direction, this height must be 4, right? So let's try to get the integral y out integral. Okay, x out integral first. Then the given integral is the same as x is moving from 0 to 2. Okay, then for each x, that is bottom y, and that is top y. Bottom y is now x squared. From this curve, y equal x squared. So for each x is bottom y, and top y is 2x. Okay, the integrand is now 1 plus 2y, and that is y direction, and x direction, the out integral. Okay. Now, to get the integral, we focus on this one. Then that is from 0 to 2, and that one is now y integration makes y and y squared. Y is moving from x squared to 2x and dx. Okay, let's evaluate the inner integral from 0 to 2. Now that is 2x minus x squared, and okay, that one is 2x minus x squared, and this one will make now 4x squared minus x to the 4, x to the 4, okay, dx. Then now for this one, this is 3x squared. So antiderivative, that is x squared, and plus x cubed, and here minus 1 over 5, and x to the 5 from 0 to 2. Okay, once it's 2, then that is now 4, 8, so 12 minus, and there's 32 over 5, right? Okay, so that is 60 over 5. So the final answer must be 28 over 5. Okay, we have the solution. Okay, now we'll try the other direction. Sometimes the other direction can be much more complicated, sometimes impossible, but anyway, let's try. Now, the y integral is the outer integral, but y is moving from 0 to 4. Then, okay, let's go back to the picture. For each y, bottom x is this one, top x is that one, right? Bottom x, okay, that is from the equation bottom x is y over 2, right? Y over 2. Top x, okay, that is y equal x squared. This position is y equal x squared. X is, from this one, x is square root of y, right? So that is a square root of y. And the integrand is 1 plus 2y, and x direction inside, and y direction outside. Okay, we have that. Now, for this one, this is now a kind of a constant because it's x direction integration. So the inner integral can be easily done. That is, integrand is 1 plus 2y, a constant, and interval length is square root of y minus y over 2. For this integral, it's not so much complicated. For example, now you can expand. Then that is now square root of y, and then minus y over 2, and plus 2y, square root of y, so that y to the 3 over 2, and then this multiplication will make here minus y squared, right? Now, from this one, for each term you can get antiderivative, and you can finalize the solution. Then you will get the same solution. Okay, so I'll stop here, but you can get it the same solution. Okay. Here, the main concern is how to access the domain D. The iterated integration must access the points in D once and only once. In either way, here, if you try to access vertically, then x is moving from here to there, and for each x, bottom y and top y. So that in vertical way, you are accessing domain and like that. But this access is now done, and with once and only once manner, you cannot duplicate some points in the domain, or you cannot miss any points in the domain. And also in y direction, after integration, then for each y, you're accessing the domain horizontally for each y, so that you can cover the domain once and only once. Now let's go back to this problem. The same for this one. Y is moving from -1 to 2 for each y. Now bottom x, top x, bottom x, top x, and in this way we are accessing the domain. Of course, for this problem, you can do you can access the domain vertically. But now, if you try to do that, then x is moving from here to there. Now, because it's a bottom, if you consider the bottom, then this bottom is not expressed as a function. So that you may try to chop the domain over there, and then you can do this portion vertically, and again, you can do the other portion vertically. Then you can access the domain once and only once. Either way, you can do that. But if you try to do this way, vertical access, then the problem will be much more complicated. So that's the reason we did only the access to the domain horizontally. Okay? Okay, and we'll continue in the second part.